Cost of electricity. So this is really a mini lesson, very mini. Has to do with billing as it relates to the cost of electricity that gets delivered to your house. So when we get charged for electricity, you actually pay for the joules of energy that get delivered to your house. But we're going to talk in just a second about the fact that we don't really use units of joules for that energy. We do use other units. And skipping ahead, I'll get to in a second. Does anybody happen to, as a matter of trivia, remember what units for energy we used when you talked about it in grade 9? It's a couple years ago now. Yeah?
Watts or kilowatts?
No, not watts and kilowatts. Yeah? Kilowatt hours. Okay, it's kilowatt hours. So we'll get to the logic for why that's used in a second. And maybe you weren't ready for that logic in grade 9, but you're ready now. You're more mature and worldly. Okay? Power we talk about as watts. So we talk about units of watts, and of course watts are joules per second if we talk about the units that are embedded within the unit that we call watts. So joules per second brings up the idea that it should be the amount of energy per second that's being consumed by a particular device. It might be a light bulb, might be a toaster, might be your dryer, might be your blow dryer, who knows? But some device is using up a certain amount of joules of energy per second. Now it might be useful to rearrange this formula to get energy by itself, so we could say that the amount of energy that gets consumed by a circuit, or a load on a circuit, would be equal to the amount of power that load consumes times the amount of time that load is in use for. And if you look at a lot of our appliances, light bulbs, whatever, you have a power rating on them. What's a really common load that has the power rating printed right on it? Light bulb. Yeah, so you might have a 100 watt light bulb, 60 watt light bulb, 30 watt, 20 watt, whatever it is, you've got a wattage rating on it. You go to look at your dryer at home, open up the door, I bet you'll have some sort of a sticker that says something like Enter Guide. In Ontario, we have these stickers that say Enter Guide. I know you'll see similar stickers in different parts of the world or in the States or whatever, but it'll tell you what the power rating is for that appliance, and it'll tell you what the rate of consumption of energy is. Anyways, in this form, it's nice to talk about the units. So we know that we could talk about it as watts times seconds. But here I want to let you in on the fact that if you have one 100 watt light bulb, that's 100 watts, right? Do you have more than one light bulb in your house?
Yes.
Most of us do. You might live in a shed, and there might only be one light bulb, but that notwithstanding, you might have as many as 10 light bulbs in your house. Can you imagine? And if you had 10 100 watt light bulbs, 10 times 100 is 1,000. Suddenly you start using units of maybe kilowatts, just to talk about your light bulbs even. So we could say that a power rating for a house might be more reasonably measured in kilowatts. Could be a house, could be an industrial application. In any case, for these large electrical systems like a house, kilowatts is a useful unit for power. And typically we talk about not running them just for a few seconds, but for maybe a few hours. Your house is in operation 24 hours a day. Why use seconds? That's a lot of seconds in one day. So we talk about hours. So it becomes reasonable to talk about units of energy as kilowatt hours. And that's something that was brought up when you were in grade 9, but maybe you didn't talk through the reasoning for it. Does the reasoning make sense? It was just maybe presented to you as a fact or trivia item in grade 9. This is just a logical statement that we could use kilowatt hours for energy units. Now, if we wanted to talk about what's unreasonable, some people say, well, why don't we just use joules? Well, let's talk about joules or watts for power, or joules per second, which would be the energy. If we talk about power in terms of watts times delta T, let's say that I have those 10 100 watt light bulbs that I mentioned earlier. Let's say you turn on 10 100 watt light bulbs. What's the power on 10 100 watt light bulbs? It's 1,000, right? Let's say that you run those 10 light bulbs for an hour. How many seconds is that? 3,600. 3,600. 60 seconds per minute, 60 minutes per hour. 60 times 60 units all work out to being 3,600 seconds if we left it on for 1 hour. We're just talking about the energy consumed by 10 light bulbs in an hour. What's 1,000 times 3,600? Yeah. 3,600,000. I heard two answers. 3,600,000 was one answer. The other answer was a lot. Either way, valid answers, but one's more accurate than the other. And so you would have 3,600,000 watt seconds. Now, which do you prefer? 3,600,000 watt seconds or 1 kilowatt hour? You get where I'm going with this? You start seeing a lot of scientific notation on your electrical bill, everybody gets upset. Okay? So we're going to go with kilowatt hours. It eliminates a lot of scientific notation. Industrial units for energy make a lot of sense in context. Okay? So in that context, let's say that we're running our house, and we've got a house that we'd like to power. Recent, or maybe not so recent, electrical proposals have said that we should have peak hours and non-peak hours or off-peak hours for electrical billing. So I'd like to propose that in a certain community at a certain time, it was stated, this is fictitious, but let's say that it was stated that $0.08 per kilowatt hour was going to be the weekends and after 6 rate. After 6 p.m. that is. Okay, or if you're military, you say after 1,800 hours. Okay? And that imply, we're going to make that imply after 6, but before 6 a.m. So we're going to put it on a 12-hour cycle. Now, whether or not our region decides to go on a 12-hour cycle or not at some point in the future, who cares? This is a fictitious situation. But let's say that between 6 p.m. and 6 a.m., it's on this rate. In the morning, at 6 a.m., the rates change, and they go up to being 12 cents per kilowatt hour. Okay, 12 cents per unit of energy. And that's going to be weekdays. And from 6 a.m. to 6 p.m. on those weekdays. I should have said from 6 to 6, not and. Okay, so we've got a rate that's going to differ, depending on the day of the week maybe, and the time of the day. And so what I'd like to propose is that we could use some of these ideas to figure out how much it costs to run certain devices. Okay? So let's pick on the 100-watt light bulb, because the 100-watt light bulb, maybe it's a dinosaur, maybe we're all going to use these CFL high-efficiency bulbs, but it's got nice round numbers to it, so that's why I'm going to choose it. It's not because I think that we all have them these days. Maybe we don't. Maybe we have the nicer light bulbs. But let's say that we have for ourselves a 100-watt bulb, okay? And you can make your bulb more fancy than mine if you like. Doesn't really matter. But we've got this 100-watt light bulb, and I'd like to propose that this 100-watt bulb is going to be run for 24 hours straight. Okay? 24 hours in total. The thing is, if it's running for 24 hours total, you look at your clock, you know that means that it's going to start at 6 o'clock, tick, 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 and then end up at 6 o'clock again, and then tick, 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 and then it's going to end up at 6 o'clock again, right? So we're going to go through 2 cycles around the clock here, 2 12-hour periods. The issue is that one 12-hour period is going to be at one consumer pricing rate, and the other 12-hour period is going to be at another consumer pricing rate if it's a weekday. So let's assume that we're running a light bulb, 100-watt light bulb, on a weekday, all day long. Good? Let's figure out the cost then. So as people talk about the cost for these things, we could say that we've got cost. If you know that the units for cost are in dollars per kilowatt hour, and you know the units for energy are in kilowatt hours, what would I have to do to those two values to cancel out the kilowatt hours? Let's look at the values again. I know that energy is in kilowatt hours and cost is in a rate per kilowatt hour, what would I have to do to this value and this value to cancel the kilowatt hours? What's the mathematical operation? Yeah, multiply them. And that's just some logic with talking about units. So I know that if I was going to come up with a cost formula, it might be something like this. It might be the amount of energy, E, times the rate that we're going to charge for energy, the charging rate. So the total cost would be the amount of energy consumed times the rate that we're going to charge people per unit of energy. Okay? Now, if I'm going to run this light bulb, the 100-watt light bulb, I need to know that E value. So let's get the E value for a 12-hour period. For a 12-hour period, we're saying that E is equal to power times delta T. And remember, we're going to use the industrial or home units, okay, for home billing. The power, we've just said, is 100 watts. And the time is going to be 24 hours. But do we ever talk about watt hours? What should it be? Thank you. 0.100 kilowatts times 24 hours. Is there anybody that can give me a value for that energy? 2.4. 2.4. Are you sure? 2.4. That's 2.4 joules. Sorry, 2.4 kilowatt hours rather. Now that's if we were talking about for the whole day. Are we talking about for 24 hours or do you want to break it up somehow? 12 hours, right? So we could do this, instead of doing it for 24 hours, we could have said energy equals power times delta T, where we're doing 0.1 kilowatts times not 24 hours, but 12 hours. And you get 1.2 kilowatt hours. And really, that's the value we want. We want to say, hey, that's how much energy we consume in half a day. Okay? We could have just said 2.4 divided by 2. But for half a day, that's how much energy we're going to consume for this 12-hour period. So now we've got an E value, this E value up here. We've got two rate values. The two rate values, let's call them R1 and R2. R1 was during the off-peak hours, and we said that R1 was equal to $0.08 or 8 cents per kilowatt hour. And rate 2, that's during the peak hours, or during the maximum usage hours, like during the day, basically when they don't want you to use that much electricity and trying to deter you by higher costs, is 12 cents per kilowatt hour. You know, and whether or not people really make use of these price differentials is, I guess, up to the individual person. Maybe you decide to run your dishwasher late at night, like my family chooses to do. Maybe you choose to use your dryer after 6 o'clock. You know, we do the wash maybe at one time, we do the drying at another time. Try to make the most of these price differences. No, maybe you don't care at all. Maybe you got money to spend. It's up to you. Really, they're just trying to lighten the load on the electrical grid because the electrical grid can only make so much. So we're trying to get people to make the choice to shift to evening usage so that we don't overload the grid or make too much demand of the grid, I should say. Okay. Anyway, we can find out the cost for peak hours and off-peak hours. I'm just plugging in values here, okay? So maybe you can beat me to it. I'm going to write down what I have to write down. You do the calculations that you know you have to do. Find the cost during peak and off-peak hours, and we'll see if our values match up, okay? So I'm going to say cost 1 for the off-peak hours and cost 2 for the peak hours to go along with rate 1 and rate 2. Oops. Okay. And if you kept up with me, or maybe you've beaten me to one of them, I've got two costs. Cost 1 and cost 2. Cost 1 being the peak hour cost, or the off-peak hour cost, and cost 2 being the during the day cost, the high cost. Yeah. Oh, I'm sorry. I wrote the wrong unit. Oh no, you're right. I shouldn't have put that unit there. I'm sorry, thank you. Okay, so we've got two costs, one for one part of the day, one for the other part of the day. And I'd like to figure out what the whole cost is for running this 100 watt light bulb for a day. So I could say, well, cost total, if you like, is equal to C1 plus C2, of course, the cost to run it during the day and during the evening, which is 0.096 or 9.6 cents plus 0.144 or 14.4 cents. Can anybody tell me how much it costs to run this 100 watt light bulb all day long? John?
0.24.
Yeah, 0.24 or 24 cents. Now, I mean, if your home is anything like mine, sometimes you get a little bit of flack. Why are you leaving on the light bulb? You think we're made of money or something? Now, I certainly don't condone being disrespectful to anybody that's your elder. But really, if you could explain it in a polite way, and maybe it's not just about the cost, maybe it's about being a conservationist, but if it was just about the cost, you could explain it in a fairly polite way potentially if these rates were what your local rates are. You say, listen, I left the light bulb on all day. Here's a quarter. Okay? I wouldn't recommend doing that. Not if your parents are like my parents. But it's good to be able to see the math. Now, are light bulbs the most energy demanding thing in your house? No. You got a washer, you got a dryer, refrigerator. That's a big culprit. Go look at the power rating on your refrigerator in kilowatt hours. Figure out how much it costs to run a refrigerator for a day. Then figure out how much it costs times 30 for the month. Fridge is big bucks. If you got a hot tub, if you're so lucky, you paying big bucks to keep that thing hot, especially in the winter maybe. Okay? So the power rating might change a little bit depending on the season for some of these things. In fact, it turns out an air conditioner works very efficiently in the winter. Maybe it's drawing less power in the winter, right? So your power draw for an air conditioner, if you let it run all winter, you're stupid if you do, but you'll save money running it in the winter versus in the summer. Go figure.